All right, as promised, we're going to be doing a few more examples to make this a little bit more clear. And the cool thing about this is that there's such an abundance of problems out there. You can practice this until you can do it in your sleep. Okay, but we're going to do two or three more examples here together, so you can get the hang of it. All right, so in this example, we're trying to get food to a desert island by doing this package drop off, right? It's similar to the example we saw in the last video. And so imagine you have a Red Cross relief plane that needs to drop several aid packages to a group of survivors named Jack, Kate, Hurley, Charlie, and Sawyer. If you get that reference, send me an email for a point of extra credit. On a remote island in the Pacific. The plane has an altitude of about 300 feet and is traveling at 127 miles per hour. Ignoring air resistance, how far should the plane be when the Red Cross crew releases the packages? Okay, very important, very practical problem. Just like we did in the last problem, we start out by making a laundry list in both the X's and the Y direction. Okay, so remember, these are two distinct, we call it orthogonal directions, and we need to treat them both totally separately. Okay, and this is the easiest way to treat them separately. So we start with the initial velocity in the x direction, v1x, final velocity in the x direction, acceleration in the x direction, distance in the x direction, and time. Okay, and then over here we have the initial velocity in the y direction, the final velocity in the y direction, the acceleration in the y direction, the distance in the y direction, and time. Once again, remember time has to be the same for both, and it's entirely possible that we'll have to solve for time in one of the other directions so that we could put it in both dimensions. Okay? All right, so the initial velocity in the x direction. Do you guys remember what it was from the last example? So if the plane's going v0, okay, the speed v0, which is 127 miles per hour, right? Then the package needs to be released with that same speed, right? The package is going at the exact same speed as the plane's going, right? So here we're going to need Siri again. Hey Siri, what is 127 miles per hour in meters per second?
127 miles per hour is 56.77 meters per second.
56.7, we'll say 56.8. You know what? We're just going to say 56 to make this problem a little bit easier. We get the hang of it, right? We get the idea. So the initial velocity in the x direction is just 56 meters per second. Now, we remember that there's no forces, especially if there's no air resistance, there's no forces in the x direction, so the acceleration at x has to be 0, which means the final velocity in x is also 0, right? Okay, cool. Now, the distance in x, this d here, this is exactly what we're trying to solve for, right? When do we release the package so that it lands safely on the island, okay? And time, we don't know yet. Okay, what is the initial velocity in the y direction? Well, it's being released without being thrown down, right? It's being released essentially from rest in the y direction. There is a x velocity, but no y velocity, so this guy starts at a very simple 0 meters per second. Right. Now, we don't know what the speed's going to be when just before it lands, right? So that's a big question mark. But we do know that the acceleration in the y direction is negative 9.8 meters per second squared. Okay? And we also know that this package is falling, so falling negative, a negative height, negative h, okay? Which, it says altitude of about 300 feet, so we actually know the value of that, all right? Which we're gonna find out again from Siri. Hey Siri, what is 300 feet in meters?
300 feet is 91.44 meters.
Thank you, Siri. 91.4 meters. We'll just say 91, just to make our lives a little bit easier. 91 meters. Not meters per second, just meters. Okay? And again, we don't know the time. Okay, so here's the deal. We want to write down our kinematic equations, which we'll do right here, right? V2 equals V1 plus AT. We have V2 squared equals V1 squared plus 2AD. We have D equals V1T plus 1 half AT squared. Okay. Now, to find D, again, similar to the last example, it would be really useful to use this equation because A is 0, right? That means that goes away. And so we could just simply translate this into D equals V1T, right? That goes away. And we know that V1 is 56, right? So this is simply D equals 56T. Again, if we just know how long this package is in the air, we know how far away the plane needs to be, D, before we drop it. Okay? So how do we get this time? That's the next thing. Okay, we don't have V2 this time, but we do have V1, A, and D. What's an equation that is V1, A, and D, and T? Well, looks to me like this one does right over here. Yes. Yes, this one does right over here. Okay, so what I want to do, so FYI, even physics professors have to think sometimes about a problem. So what I want to do now is I want to say dy equals v1t. Well, what's my v1 in the y direction? It's 0, right? So that's just 0 plus 1 half times negative 9.8 times t squared, right? Okay, now we know what this dy is, right? We had calculated it. Siri told us a second ago it was negative 91. So I have negative 91 here, right? And I know that 1 half of 9.8 is 4.9, so that's negative 4.9 t squared. Okay, if I now just solve this equation for t, what do I get? I get a glorious 4.3 seconds. So this package is woo, in the air for 4.3 seconds before it lands. But now that I have that, I could very easily just put that in here for my time, right? So this is going to be 4.3 here and 4.3 here. And I put that in and I get 56 times 4.3. We have to be exactly 244 meters away from the island to get the relief package there so that it lands directly on the people. Okay? Well, hopefully not on the people, if you know what I mean. But that's how that works. All right. That's 2 examples down. I hope this is becoming a little bit more clear. This video is, well, actually, I was just really curious. Do human cannonballs actually exist? Because it seems preposterously crazy. And it turns out they do. And I will be attaching this video into the module, so you can watch that there. I do want to mention a projectile motion shortcut. In cases where an object is launched and lands at the same exact height, okay? So it's launched from the ground, lands at the ground, right? This is the only case where this works. But in this case, okay, you can say that the range is always going to be equal to the square of the initial velocity, right? So whatever the initial velocity is, divided by gravity, times sine of twice the launch angle. Okay? Now, just to warn you, once upon a time, I shared this with students, and I gave an example on a test where the initial height and the final height weren't the same, and everyone used this formula anyways, and everyone got it wrong. So be careful, don't do that. This is just a way to, to simplify things when it's possible. And I totally encourage you guys to go ahead and try to derive this on your own. Why is it that if these start and end at the same height, this ends up being the formula all the time for the range? Okay? So go ahead and look into that. Okay. We have two more worked examples to do, but I feel like this video already went on pretty long, so I'll see you in the next one.